Hello everyone, my name is Dongdong. It is my pleasure to talk about DDP-based parachute landing optimization for humanoid. This paper is co-authored by Yang Liu, Yifan Xing, Shamna Ghosh, and my advisor Vikram Kapila. We are from MCRL, Tandon School of Engineering in New York University. Let's talk about the background of this paper first. In an extreme disaster environment, such as earthquake or wildfire, we want to deliver humanoid for rescue mission instead of human to avoid loss of life, because humanoid is built to be flexible as a human being. However, humanoid delivery to a disaster site can be difficult, since land transportation may be unavailable. For example, the bridge may be destroyed by the earthquake, or the road may be blocked by the fire. We may consider delivering a humanoid to a disaster site like a paratrooper. One of the critical problems for aerial deployment is how to reduce the land impact on humanoid, since it may damage its key components such as sensors or computation unit mounted on the torso. Prior research on parachute landing with humanoid considered only one leg motion, without optimization. To further reduce the impact, we propose to use a differential dynamic programming method for landing optimization in a humanoid. In this slide, we will talk about our optimization framework. Typically, humanoid has joint space with high dimensions. For example, our biped has 12 degrees of freedom. As you can see in the joint structure, we have 3 degrees of freedom in the hip, row pitch ER, 1 degree of freedom in the knee, and 2 degrees of freedom in the ankle. Thus, it's very hard to find a feasible trajectory with the whole body model. In our paper, we seek a cascade optimization framework to address this issue. First, we try to optimize with a simplified model, which has low degrees of freedom. Then, we try to optimize with a whole body model to track the trajectory obtained from the simplified model while satisfying the contact constraint and the friction constraint. In this slide, let's introduce the approach to solve the optimal control problem, differential dynamic programming, or DDP for short. A typical optimal control problem can be divided into two parts, cost function and constraint. The cost function can be formulated as the sum of integral cost terms and terminal cost terms. The constraint is shaped by ordinary differential equation of the robotic system. Next, let's talk about differential dynamic programming approach. At first, we start with the initial control gas. Then, we integrate the current system with the initial control gas to obtain the trajectory of states. Next, we perform a second-order approximation of optimal control around the trajectory of states and controls to obtain a sequential quadratic programming problem. Then, we solve SQP recursively in a backward direction to obtain this new control. After that, we go to step 2 and integrate the current system with the new control to obtain the trajectory of the states. We do the second-order approximation and solve SQP again. We do this iteration in a loop until the trajectories converge. In this slide, we will talk about the simplified model. We use an inverted pendulum model with flywheel, or IPWF for short. It can be used to model a humanoid with consideration to momentum. It consists of a massless telescope link with a flywheel centered at the center of mass. The flywheel is added to represent the rotation of the torso, and the link counts for the stretch and contraction of the legs. In this model, we consider the coupling between the inverted pendulum and the flywheel by using the dissipative moments tau theta and tau alpha. The equation of motions assembled in a state space model and presented to the right. Here we provide the cost function for IPWF. In the integral cost term, LK, W1 corresponds to alpha minus alpha f, which guarantees the center of mass while forward to the desired position. And in the terminal cost, capital W1 is used similarly to penalize alpha minus alpha f Next, W2 and capital W2 in the integral and terminal cost penalize the center mass velocity to decrease it while landing. Moreover, W3, capital W3, W4, and capital W4 in the integral and the terminal cost are used to guarantee that the robot can reach a desired position theta at zero angular speed. Now, W5 and W6 are used to penalize and minimize the control actions, F and tau. Finally, W7, W8, and W9, capital W5 and capital W6, are used to bound the telescope leg length R, alpha, and torque within the upper and lower bounds by using the boundary cost function BH. Here is the whole body model. After solving the simplified model, we use a full model to command the robot to track the trajectory while considering the contact and the friction constraint. The first equation shows the whole body dynamics. M is the inertial matrix. H collects the Coriolis, centrifugal, and the gravitational forces. Gamma is the joint torques. S is the selection matrix. Lambda is the contact wrenches, and G is the contact Jacobian, which maps the contact wrenches of any factors to the generalized coordinates. For the contact, we basically constrain the any factor velocity to be zero and differentiate it to obtain the second-order terms. For the friction constraint, we use a linearized parameter friction coin to estimate the true friction constraint. Here is the cost function for the whole body model. The first and second terms are the regularized quadratic cost function that penalize the system states and controls. GF represents the friction constraint by using the boundary cost function. Gtask is the term to track the solved trajectory with the simplified model. Gtask can be divided into three parts. The first part is to ensure the center of mass in the full model to track the solved trajectory with IPWF. The second part is to guarantee the torso rotation in the full model to track the solved rotation trajectory of flywheel with IPWF. The last part is to constrain the feet on the ground. This slide shows our optimization results. We use a DDP-like library called Crocodile to solve these problems. First, we solve the optimization problem with IPWF, and then we solve a second optimization problem with whole body model. The center mass trajectory with IPWF is shown in the left figure, and the right two figures show the solved trajectories of joint positions and joint torques with full model. The bottom picture showed the timeline snapshot for the whole body trajectory. To verify the quality of solved trajectory, we tested with 12 degrees of freedom bipedal robot. We mount IMU on the torso to measure the linear acceleration when the robot touches the ground. We also have a built-in encoder in each motor. Next, we build a test bed by following the paratrooper training device. The test bed consists of a roller track set, electromagnetic holder, and approach sensor. First, the robot slides down from the left and accelerates to a certain speed. When it reaches the approach sensor, the electromagnetic holder will release the robot. In the next slide, we have a video to demonstrate this process. In this slide, we basically show the experimental results. We did two comparison experiments. One is the unplanned trajectory, designed by following the prior work. The other is planned by our proposed method. by using DDP. As you can see in the figure, the proposed method yields a 58% reduction in maximum acceleration compared with unplanned method, while maintaining a balanced state for the 12 degrees of freedom humanoid. Conclusion and contributions. So in our paper, we used the IPWF model with DDP to first plan a trajectory instead of using a heuristic parachute landing for motion. We also solve a full body motion instead of considering only one leg of humanoid, like previous paper. When we solve the whole body motion, we consider the contact constraint and the Coulomb friction constraint. Finally, we implement our optimization method on 12 degrees of freedom humanoid testbed and show the effectiveness of our proposed approach. We want to acknowledge our sponsors for supporting our work: National Science Foundation, iTest, RET, DRK-12, New York University, NASA New York Space Ground Consortium. Thank you for your support.